Okay, we're gonna start electromagnetism lecture for today's class after the episode that I have had due to COVID-related results. So yeah, we're gonna go through this sequence. The actual topic electromagnetism, that by the way I teach, is actually quite big because I have summed up all the bullet headings or the topic headings which are included. Just a second. Yes. I have summed up all the bullet headings which for which all the questions come up together in the question. So that actually covers at least three of the chapters in our syllabus, which I'm going to show you just for a while. So I'm currently doing all of these headings: magnetic fields, electromagnetic induction, alternating currents. All of these three topics for the A2 syllabus. If I go for actual syllabus topics, detail part,
Sir,
yes,
sir, please sit.
no, not yet.
Sir,
ঠান্ডা
control
লাগছে?
of allergy.
Yes. This should be 22, 23, and 24. These are the three things which I'm going to teach together, which can sum up to quite a lot of stuffs, but I'm going to make it easy for you. They're very much correlated. So it starts from here, concept of the magnetic field. And here we have one thing, that is nuclear magnetic resonance imaging, which is a part of the application feature for magnetic fields, which I'll teach further down the line. এটা পরে পড়াবো, এটা এখন পড়াবো না. Then we have laws of electromagnetic induction. Then we have the characteristics of alternating currents. So how does, because electromagnetic fields, changing electromagnetic fields and AC are very much interrelated to each other. So these things are taught, I preferably teach together. And that's pretty much it. Then here is quantum physics, and then we have band theory and X-rays and other stuffs. এগুলা অন্য চ্যাপ্টারের জন্য. So I'm going to start. There are a couple of things that I would like you to help you remember from your O levels about the magnetic field and magnetism stuffs. These things are not, I mean, magnetism was not at all introduced or included in Ayanika. Anika Tawatsumbonna. Yeah, better. আমার কথা কি ক্লিয়ারলি শোনা যাচ্ছে? মানে বোঝা যাচ্ছে?
জি স্যার।
আচ্ছা. So there are a couple of things that I like to help you remember from your O-level syllabus about the magnetism chapter, because it was not at all included in our AS syllabus. It was completely forgotten. Very much like thermal. Thermal was in our O-levels by a little bit. Then in our AS syllabus, it was altogether skipped up. And then in A2, it shows up in a much bigger version. Magnetism also happens to have the same characteristics. A couple of things we need to recall. I'm going to say up a bunch of information. I'm going to go slowly. I need you to recall and refresh your memories about these stuffs. Primarily, there are two types of substances: magnetic substances, non-magnetic substances. There are three elements which show strong magnetic properties. These are iron, cobalt, and nickel. Sometimes they are also called ferromagnetic materials. The word ferro comes from the name iron, which is ferrum in Italic or Latin, I don't know. So ferromagnetic means strong magnetic field representing elements iron, cobalt, and nickel. Because of the redundancy of or availability of iron in earth crust, As mineral, we preferably make all of our magnetic stuffs with iron. Nickel and cobalts are not used very commonly because they have other valuable usage in other parts of the industrial applications. Iron, how then again, iron can be converted. It can show two type of magnetic behavior. One is the soft magnetic behavior, and there is the hard magnetic behavior. Soft magnetic behavior is such as that it would become magnetized very easily. It would be normally demagnetized. Naturally, it would show no magnetic behavior at all. So it would be naturally of zero magnetism, but it can be magnetized very easily under the influence of a magnetic field or another magnet, and it can be demagnetized very easily as well. It will naturally try to remain demagnetized, but if you bring a magnet close to it, it will immediately become induced by the magnetic field and behave as a magnet. And its magnetism is reversible, changeable, and it is uh, it is sort of like beacon call for our requirements. If we want this magnetism to exist, we can make it into come existence. If we want it to vanish, we can make it to go vanish. So we can magnetize and demagnetize it very easily. That's the soft magnetic material, soft magnetism. And the hard magnetism is the type of magnetism where a material shows uh, retaining capability or storing capability of magnetic behavior. It tends not to be magnetized very easily if it is primarily demagnetized. It doesn't have any magnetism to start with. Or if we can somehow convert it into a magnet, then it tends to not become demagnetized very easily. So it will try to retain or store or hold on to its magnetic behavior further down the process. These are the two types of magnetic behavior that we have. We're going to require to understand both of them. And we'll use both of these magnetic behavior. The reason different type of iron itself can work as both of these material. It depends upon what are the alloy constituents of the iron thing that we are using. Typically, higher carbon content give us higher carbon contents, give us more soft magnetic material. For example, cast iron. If we have cast iron are usually directly made from the blast furnace, which is the furnace that we use to make liquid iron out of the ore. It usually has a lot of carbon content within itself, which can work as a soft magnetic material most commonly. And then we can have steel. Steel is a much more refined version of soft iron or cast iron, and that usually has a much smaller content percentage of carbon, and that can work as a hard magnetic material more strongly. You don't have to understand or remember the constituent parts. This is just something that I added up to give you some interest about the topic. It's just that iron itself can behave as both of these materials, soft magnetic material and also hard magnetic material, depending upon what other element, namely carbon, is present by how much percentage in its alloy. Depending upon that, it can show us both of these behavior, soft magnetic or hard magnetic material. So that's just another part. The next thing that we need to remember, there are a couple of things that I'm not going to brush up the entire syllabus of the O-levels because certain parts are not at all required for our requirement. Audit, are you here? Hello? Is Auditro here? অরিত্র কোথায়? আচ্ছা, নেভার মাইন্ড। অরিত্র আব্বু কল দিচ্ছিল আমাকে। আচ্ছা, I didn't pick it up. আনিকা, আনিকা তাবাসসুম বন্যা, এটা কি আমাদের যে গ্রিন হেরাল্ডের আনিকা?
জি স্যার।
আচ্ছা, তোমার চ্যানেল থেকে মাঝে মাঝে অনেক হাই কোয়ালিটি ব্যাজ আসতেছে। It's not disturbing, but it can be fuzzy sometimes. Like
স্যার একটু আগে ওটা অ্যাড ছিল ফোনে, সরি।
ও আচ্ছা আচ্ছা, ইটস ওকে, সমস্যা নাই। Just be careful, তাহলে হবে।
জি স্যার, শিওর স্যার।
I'm not going to help you remember or recap all the parts of the O-level syllabus because all of those parts are not required for us. So I'm directly now jumping into the electromagnetism topic. One of the primary thing that I need all of you to understand and remember that electromagnetism is an exhibit property of electricity. It is not an exhibit property of the conductor. I'll go again. Electromagnetism is an exhibit property of electricity. Whenever charges will flow, current will exist in whatever conductor that is. There will be a simultaneous presence of magnetic field, which is an output of flowing charges. These flowing charges can happen in any mechanism. It can also happen without any conductor for all I care. Charges flowing, charges moving from one place to another place will give rise to current, and current will have a subsequent effect, simultaneous effect of magnetism. So what I'm trying to mean is that if you have current flowing through a copper wire, you will have electromagnetism around it. If you have current flowing through an iron wire, you will have electromagnetism around it as well. If you have current flowing through a graphite rod, you'd have electromagnetism around it. If you have current flowing through an electromagnetic solution, let's say in an electrolytic solution, if you put it in a long cylindrical tube and make some current flow by putting two electrodes on the two sides, there will be effective current flow through that tube. That will also produce electromagnetic fields, magnetic fields around it, which is what we call electromagnetism. Point that I'm trying to make, the conductor is not primary. Conductor doesn't even matter. It is, what really matters is the presence of flowing charges. Charges moving means there is a current. Current essentially gives rise to magnetic fields. That's why we call it electromagnetism. It is not dependent upon the conductor. It is dependent upon the incident of current. And as we've learned in our O levels, we have learned about two different experiments and laws as well. One of them was Faraday's law. The other one was Lenz's law. I'm going to help you remember them a little bit, and then we're going to see about some mathematical calculation about those things as well. Faraday's experiment essentially gave us three ideas. Three. Scientist Michael Faraday did a lot of experiment on current flow, and finally he published his findings in two different setups. I'm going to explain those two setups individually for all of you. Let me find out some figure.
Sir?
Yes.
Oh, yes, sir. You can use FET simulations. They're great.
Fit.
Yes, sir. The first one.
Okay. I'll
They
try.
have a bunch of other experiments as well, which are equally good.
Okay. Okay. Do I download or play?
You can play it, I guess. It should
Yes,
work.
sir.
Oh.
Yes,
Okay.
sir.
This is one of the simulation that goes up for Faraday's experiment. This is one of the this is the way I usually go for it. Is this the second set of finding that in which he expressed his finding for a coil. The way it works is that if we have a magnet and if we move around a magnet close to an electromagnetic coil, in that case we can induce a magnetic field around it. Have a look. We can make the magnet move around in either direction. So the basic idea that this current generation or EMF induction over here is that if this coil can be somehow subjected to, can be somehow experienced, can be somehow made to experience a change of magnetic field strength around it. জিনিসটা বুঝো. If this magnetic field strength can be somehow made to experience a change of magnetic field strength that exists around it. Now, if you wonder what the hell is the magnetic field strength, magnetic field strength is a defined quantity which we're going to define after a while. It will show up in your syllabus, Don't worry about that. For the time being, what I need you to understand as for magnetic field strength is about the closeness of magnetic field lines in a magnetic field line diagram. So if you try to visualize a magnetic field diagram over here, you can try and imagine there are magnetic field lines which are coming out from the North Pole and they are going into the South Pole. So they are making elliptical shapes like Mishti Kumra or a pumpkin or something like that. And the closer the field lines are, the stronger is the field. The farther the field lines are, the weaker is the field. That we know for all very well. Now, whenever the magnet is placed over here, this region is experiencing a certain thickness or is experiencing a certain strength of magnetic field. There is a fixed value. It is not changing over time. If I move the North Pole closer to the coil, I mean, let's say initially the North Pole was further, now I'm moving it closer. In that movement, this coil will experience a change of magnetic field strength from a weaker magnetic field to a stronger magnetic field, because I'm bringing the more dense pole or the stronger, closer region of the magnetic field lines closer to the coil. I don't have the magnetic field lines drawn over here in this animation, but I want you kids to visualize this magnetic field lines like this. Let me just show you a figure so that for those.
স্যার ফিল্ড লাইন্সের স্যার ওখানে টিক মার্কটা স্যার ক্লিক করলে স্যার আপনার ফিল্ড লাইন্সটা শো করবে।
Really?
Yes, sir.
Yes,
There was
sir.
a checkbox.
Oh, amazing. Sorry, I was blind. My bad. Thank you. So this is what I'm talking about. So whenever the North Pole is pretty far away, the magnetic field strength over here is pretty weak. The moment we are bringing the North Pole closer, this coil is experiencing a shift of the magnetic field strength that exists around itself from a weak magnetic field to a strong magnetic field, and which is giving us a change of magnetic field strength. And that is basically why the current is generated. This is the underlying reason for how we explain why EMF is induced in this kind of movement. Another way to explain the exact similar concept, is that we can say that whenever the magnet is moved, or I cannot move the coil over here. Okay, whenever the magnet is moved, the field lines will cut across the magnetic field lines. Have a look. This field line, let's have a look at this field line, this one that is continuous over here. You see, whenever I'm moving the magnet in, I can maximize this. Yes. Does this help? No, it doesn't help much. Okay, fine. For example, let's say in this orientation, this field line is now cutting across this first coil. As I'm moving over here, this is cutting out the second, and then the third, then the fourth. And practically speaking, these magnetic field lines are hypothetical representation of the existence of the magnetic field. There exist, I mean, magnetic field lines or any type of field lines, for all I care, for all that matter, are actually hypothetical lines. They're used to represent the existence and orientation of a certain field. It can be electric field, can be magnetic field. So to be honest, there are no such lines. We are only using them to represent a relevant arrangement and strength of the magnetic field around a certain source. For example, an actual magnet that is existing over here. So whenever we're going to move this magnet around this coil, we're going to make the field lines cut across the coil. And that cutting is what produces the current. That's also another way to physically explain the EMF generation in a coil because of the movement like this. So Faraday's experiment gave us 3 basic ideas, all of which can be summed up in one single sentence. I'm going to tell you the 3 different observations that he published, and then I'm going to tell you how they can be merged into one single sentence. The first thing he said is that whenever the magnet is moved closer or further away from the coil, we can see there is a current EMF generated in the coil, and it is only available as long as the movement is happening. Whenever the movement is stopped, the current flow also stops. So as long as the movement is happening, the current flow is happening. This is the first observation. The second observation is that closing in the North Pole gives us one type of EMF. Have a look. If I'm bringing the North Pole closer over here, the EMF is happening to the left, and then if I'm moving it to the right, it is happening to the right. So the second statement was like this, that changing the pole or changing the movement direction reverses the EMF orientation, which means that I can bring the North Pole closer in. We're having a negative EMF. The galvanometer is over here, lifted to the left, so I'm naming it as negative EMF. And then if we move it to the right, we're having positive EMF. Other than this, if we do the opposite thing, if we flip the South Pole, then if we move it to the left, then we're going to have a positive EMF. And then if we move it to the right, then we're going to have a negative EMF. So doing one of the changes, either of the changes one at a time, will give you a reverse of the EMF. So if we reverse the movement direction, it will reverse the EMF, or if we reverse the pole, it will also reverse the EMF direction. So if you change both, there will be no change, because there will be double reversed. So you will get the same orientation, which should make sense. The third observation for Faraday's experiment was, so the first, I'm gonna repeat the first once again. The first one was that moving the coil, as long as the movement happens, induces the EMF. Movement stops, no EMF. That's the first observation. Second observation, reversing the pole orientation or the movement direction reverses the current EMF induced in the coil. Third observation, faster movement gives more EMF, slower movement gives less EMF. So all of these three things can be merged into one single statement, and that statement being, it is the rate of change of magnetic field strength. Rate of change of magnetic field strength, or magnetic flux linkage to be more applicable term, which we're going to define in a bit. It is the rate of change of magnetic field strength that actually causes the EMF generation. Or in other terms, we can say that the EMF induced in a coil is directly proportional to the rate of change of magnetic flux linkage. Magnetic flux linkage is a certain term which is relevant to how much magnetic field of this magnet is actually affecting this coil. It's somewhat related to this. For example, this magnetic field around the magnetic field is traversed all around itself, I mean, in a huge space. But by moving this magnet close and far, we're not making all of the magnetic field, I mean, for all the space which is on the top, all the magnetic field which is located on the bottom, we are not making all of these things to cut across the field lines. That is not happening. Sorry, the cut across the lines. So that is not happening. Because that is not happening, so there is a certain measure that how much of this available magnet, or how much of this available magnetic field is actually relevant for this coil. That quantity is what we define as magnetic flux linkage. We're going to talk about them. We're going to show them in a bit later. So these are the three observations for Faraday's electromagnetic experiments, and this is what we call Faraday's electromagnetic law, which is related, which is once again for the last time, is stated as the EMF induced in a coil is directly proportional to the rate of change of magnetic flux linkage across that coil. Yes, Avias, go ahead. I'll take questions now. You can raise hands. Avias, bolo.
Sir, I have a question. You said that feelings are imaginary, but when we do the iron feeling test, it kind of seems like there's actual field lines that where the field strength concentrates at.
Those iron fillings actually represent us a certain orientation of those, of the alignment of those iron filling of the iron fillings. The reason we are saying that the field lines are imaginary or they are inexistent, because we cannot ever physically find out those lines. Using the iron fillings, we can make this orientation come into existence, because each of those iron filling will be induced into a small magnet. They will together work to give us an orientation like this. If you do the same experiment with the same bunch of iron fillings and the same magnet 10 times, you will never get two identical figures. If field lines were actually physically existing lines, then we should get some figure exactly identical to each other, but you are never going to get two identical figures. No matter how many times you do this experiment, they are never going to be exactly identical, proving us that the field lines are not practically existing things.
Makes sense, sir.
Okay, Fardin.
And the iron fillings, the arrangement is always random.
Yes, it is always somewhat different from each other, and it is located, it is highly dependent on exactly in which location those iron fillings are, or if you sprinkle on a piece of paper those iron fillings, how finely or how well are you sprinkling those up. It is dependent on the exact location of the iron fillings at that instant of falling on the paper. That's what defines their individual creation of that shape.
Okay, sir.
Sure. Pardon.
স্যার আপনি কি ম্যাগনেটিক ফ্লাক্স লিঙ্কেজের ব্যাপারে একটু বলতে পারবেন? আমার কেটে যাচ্ছিল।
হ্যাঁ, ম্যাগনেটিক ফ্লাক্স লিঙ্কেজের ব্যাপারে ডিটেইলস আরো বলবো। ফ্যারাডেজ লটা আলটিমেটলি যেটাতে তিনটা অবজারভেশন যেখানে সাম আপ করতেছি আমরা, সেটা হচ্ছে যে the EMF generated in a coil can be said to be proportional, that's what Faraday's law is,
Directly proportional
to the rate of change of magnetic flux linkage. এটা magnetic flux linkage জিনিসটা কি সেটা আমি এখনো কোয়ান্টিটি হিসেবে ডিফাইন করি নাই, এটা আমি একটু পরে ডিফাইন করব। But what I wanted to get out from this discussion is that it is the change of magnetic flux strength, magnetic field strength across the coil, which is responsible for the magnetic field, which is responsible for the induced EMF. If you make the change from weaker to strong, you're going to have one type of EMF. If you make the change from strong to weak, you're going to have a reverse type of EMF. So it is all dependent on what type of change are you making, and because faster movement gives you more EMF, slower movement gives you less EMF. That also tells us that what is the rate of your EMF, of your magnetic field strength changing. That is also a predominant factor for how much EMF are you going to get. If you can make that change over a short period of time, if you can make that change really fast, you're going to have a high EMF. If you make that change slowly, then you're going to have a low EMF, something like that.
Yes, got it, sir. Thank you.
Sure. So that was about Faraday's law, or Faraday's experiment, and then came the Lenz's law. Lenz's law was actually a very what can I say? In Bangla word, if I say Jugantokari proposition, because when electromagnetic induction was first developed, there was a huge turmoil in the scientific community that we have altogether. As human species, we have defined that energy and mass, they are conserved quantities, which means they are not going to change. They're not going to change. This essentially means that if we are trying to create energy in any place, it will be a fixed amount. So what was seen in this case of magnetic field EMF is that whenever the magnet was moved around the coil, we could produce some electrical energy, whereas this coil was not physically connected to any of the source whatsoever. So where is this energy is coming from? Is energy is now being created? And then Lenz's actually gave us a solution that what he said that no, energy is not being created. It is this kinetic energy of this coil, magnet, in this case for this animation magnet, or we could alternately keep the magnet stationary, and if there is a certain way we could move the coil around, that would also be possible, which is also a certain design aspect for many of the AC generators that we have. There has to be some sort of relative motion between the magnetic field and the coil. That's all that matters. You could move the magnet, you could move the coil, or you could move both of them in opposite direction simultaneously. That's also depends on how you want to design this field. So what Lenz's law tells us that whenever this movement of magnet would be done, this will essentially cause the EMF that will be generated within the field, within the coil, and the EMF will always be generated in such a way that this motion of the magnet will be opposed. Get this point straight. This is sort of like a bit of like elasticity. If we have a rubber specimen, if you try to extend it, it will try to pull yourself back. If you try to push it, it will try to push yourself out. So it will always try to resist that deformation. This coil will also produce an invisible force like an elastic rubber. If you're going to try to bring the magnetic field not pull closer, this coil is going to try to oppose this motion. It means it is going to try to push out this magnet in the outer direction. And to make this motion possible, we have to work against that reversed force or the opposing force that is generated from the coil. Similarly, if you're trying to make this pole taking away from the coil, it will try to attract that north pole. it will try to pull that North Pole closer. And we have to make this movement possible to take it further away. We have to work against that force, attractive force from the coil, which means the coil will always try to oppose the motion of the magnet that is causing it to induce some EMF. Always. This is essentially where the idea becomes very interesting, is that whenever we're going to do some work against a force, when we're going to do some movement, displacement against a force, we have to do some work. What Lenz's law tells, or what scientist Lenz told us, that it is that work that we are doing against this force is what is being created as electrical energy in the coil. So every bit of work that we can do against this resistive force is going to be converted into electrical energy in the coil. So if we want to increase the amount of electrical energy output, we have to increase this amount of work done. Now work done is defined by force into displacement. So there are two different ways we can go for this. We can either have bigger force, small movement, or we can have small force, bigger movement. Or if we go for the big shot, we can increase both the resistive force and both the displacement, and that way we can make really large amount of electricity. This is actually the basic principle by which large megawatt level of power electric factories, electric factory to na, power stations, they work upon. They have coils which are made up of a lot of wires. They have coils which are made up with a lot of loops, so that each loop will give you a small bit of force. So together, whenever you have a long loop, large sequence of loop, you can get a huge amount of force. And because you have such a long loop, the amount of movement that you could possibly do for that magnetic field variation is also extremely large. Together, they produce a very huge amount of electricity. This is actually a very crude idea, or a very basic idea for how the electricity can be created. But the actual mechanism is far too advanced and far too
স্যার এই পার্টে কথাটা একটু
optimized.
কেটে গেছে, একটু রিপিট করতে পারেন?
কোন পার্টটুকু, কোনখান থেকে শোনো নাই?
ওই যে স্যার আপনি বললেন না ইটস আ ক্রুড আইডিয়া, তার আগে কি কিছু একটা মিস গেছে স্যার।
কতটুকু পর্যন্ত শুনছো সেটা একটু বলো, তারপরে থেকে বলতেছি।
স্যার আপনি বলছিলেন যে কয়েলটাকে হচ্ছে মানে we have to take the movement of the coil in such a way that we can produce a large amount of energy.
Yes,
that is where it got এখানে
আচ্ছা,
যে কিছুটা কেটে গেছে।
so we can produce a large amount of energy by making a huge big amount of work against that resistive force. So there are two different ways we can go for. Is we can either increase the force and with a small amount of displacement, F into X, that is the work done formula. So you can increase the F, or we can increase the X, or if we can increase both of them, F into X. So if we increase both the resistive force that we have to work against, and if we increase both the displacement, for how much movement are we going to make to overcome that force, we can really make a really large amount of electricity by doing a huge amount of work against the magnetic field. So Lenz's law tells us basically about the way Lenz's law is stated. It goes like that anytime EMF will be induced in a coil, it will be always induced in such a way that the reason of the EMF induction can be opposed. And this brings us a small minus sign in the Faraday's equation. So what is this minus sign is about? I'm going to tell you about this after a while. Let me just get into the whole idea. So this is the Faraday's law explanation that we had to recall from our old syllabus. And from this point, I'm going to start the fresh content for our A2 syllabus, which is going to get started from here. I'm going to give you this note after a while in our group chat. We'll be also including in your worksheet volume as well. Don't worry about that. So we have a couple of topic headings over here. You don't have to bother about this list for the time being. Let's try to understand how we define B. B is the symbol for magnetic field strength, or magnetic flux density, or magnetic field intensity. This single quantity has three different names, can show up in three different names in your question. They are all mouthfuls, but you just have to remember them. B is a symbol for magnetic field strength. This is the most common symbol that we use, but it is also called magnetic flux density. It is also called magnetic field intensity. Three different names. I mean, scientists did name them by three different names, so there is nothing I can do about this. This quantity has a lot of use in a lot of places, but there is a certain way that the scientists have decided to define this quantity, and that definition goes on like this. Here is a certain figure that we are having. Let's say these arrowheads, they are all representing a certain magnetic field, which is being created by a magnetic existence. Let's say here the magnetic field lines are representing from left to right, going with arrows from left to right. So assume that we have a pretty large north pole on the left side. Try to assume that, and we have a pretty large south pole on the right side. So magnetic field lines are all traveling from left to right. We haven't shown the magnetic field, the north pole and the south poles over here for the sake of simplicity of the figure, because it's not essential that we should only have north pole and south pole, physical permanent magnets, to produce magnetic fields. Magnetic field lines can be also very easily produced by a coil of wire, which we call a solenoid. So it's also possible to be created by solenoid. So the magnetic field could be produced by any way. It could be an outcome of a permanent magnet. It could be an outcome for a solenoid, for an electromagnet. But irrespective of the source, let's assume there is a magnetic field which is existing from left to right in this orientation. And this is the width of the magnetic field, from the top line to the bottom line. Across this magnetic field line, let's say we have placed a piece of wire. This line over here is representing a piece of wire which is carrying current in this direction. So this diagonal line over here is representing a straight current carrying wire which is happening in this direction, and the length of this wire which is cutting across the magnetic field line is, let's say, L, and the angle this current is making with the magnetic field line. I mean, if I'm using the word current because I could have said the angle this wire makes with the magnetic field line. They both mean the same thing because the current is flowing through the wire, so there is no harm saying that the current is making this angle with the coil. So that would be theta.
Sir, the lines here are actually field lines, right?
The horizontal lines are the field lines, and the diagonal arrow represents the current flow direction, or the conductor that is carrying the current. Okay, so whenever this will happen, we can essentially find out, do you understand that whenever a current carrying wire will cut across magnetic field lines by Fleming's left-hand rule, we can find out the force direction, but there will always be a force that will be created within this wire, and the magnitude of this force can be calculated by Faraday's by a formula which is given by this equation. The creation or the deduction of this equation is not included in your syllabus volume, so I did not go for the derivation of this equation. I have directly given you this equation, that this force that this wire will experience can be given by B into I into L sine theta. Now, one thing that I can logically explain to you that why this has to be sine theta, this is because you have to understand this thing, that for the force to exist between on the wire, the current must cut across the magnetic field lines. The current must cut across the magnetic field lines. This is very important. If there is no cutting, then there would be no EMF, which means if somehow the current flow line and the magnetic field lines are parallel to each other, or they are going in the similar direction, they are both horizontal. Let's say if this wire was aligned in this way, then this theta value would become 0. If theta becomes 0, then sine theta will also become 0. Altogether, the force would become 0, irrespective of the value of B or I or L. So to make the force exist, the current has to somehow cut across the magnetic field lines. The more bigger angle it can cut across, the more would be the force. That's why the angle sine theta is involved. It is the sine theta which is going to cause us to determine how much force are we going to have for a setup like this, from a setup like this. If the theta is 0, then the current would have no cutting. That would mean the wire is now parallel with the magnetic field lines. There will be no force. If this theta is 90 degree, which means whenever the coil wire will be placed exactly vertically or perpendicular across the magnetic field lines, you would have the most amount of cutting. And in that case, you're going to have the strongest amount of force or biggest amount of force. So that's why this formula is this is exactly how the formula is simplified over here. When theta equals to 90 degree, so that sine theta becomes 1, F equals to BIL. From this equation, if we subject the B, which is magnetic field strength, we get F divided by IL. So this is that equation from which we define the magnetic field strength. This is the equation from which we define the magnetic field strength. For example, it says over here, B is defined from this equation. B is defined as F. B is defined as F. So B is defined as force when I and L are of unit magnitude, which means if I equals to 1 ampere, L equals to 1 meter, and theta equals to 90 degree, then we can say B equals to F. This is very much similar to what we have experienced for the F equals to ma equation, the definition of Newton. Because remember that we did get ma equals to k into F in Newton's second law. Anybody remember this? Ma equals to kf. One.
Sir, m equals to kf. এটা নিউটনের লয় না স্যার?
হ্যাঁ, Newton's second law. Do you remember this?
Yes, sir.
So ওইখানে আমরা এই কাজটা করছি। আমি জাস্ট একটু রেফারেন্সের জন্য দেখাচ্ছি এই জিনিসটা, খেয়াল করো। Newton's second law told us what? That change of momentum. Sorry. Newton's second law tells us that force was directly proportional to rate of change of momentum. So this could give us this F equals proportional to F equals to K, sorry, F equals to K into M into delta V by delta T, which gives us F equals to K into M into A. So this is what we got. This is what we did get. So from this equation, we define how much should be 1 Newton. We define this equation, we define 1 Newton in such a way that if we define that if M equals to 1 kg, in that case, if A equals to 1 meter per second square, in that case, the amount of force that will be making us to make this happen will be defined as 1 Newton. This was all defined in such a way so that ultimately from this equation we could get 1 equals to K into 1 into 1. So which gave us K equals to 1. Basically, this whole equation becomes what? F equals to MA. So we chose the definition of a unit in such a way, just a second. We chose the definition of a unit in such a way so that the constant could be obliterated. So this is one of the ways by which scientific stuffs work, which for to make things easier. Just a second, to wait, Coro. So that's essentially what we're doing over here. We're going to define B as the value of F whenever I equals to 1, L equals to 1, and theta equals to 90 degrees. So this is the whole definition that goes by. Force experienced by a unit length wire carrying unit current placed perpendicular to the magnetic field lines is the magnetic field strength of the magnetic field. এখানে B বারবার লিখছে কারণ হচ্ছে আমি যে প্রমাণ দেখে এখানে লিখেছিলাম যে এই জিনিসটা তিনটা নাম আছে, কোথায় যেন আছে, এই যে magnetic field strength, magnetic field intensity, or magnetic flux density, they are all called B. This is the one place I made the kids write this name, and I said that I'm not gonna write this whole name ever again in the whole note. I'm gonna be only using the symbol B, but every single place you see the B, you have to remember that these are the name of this thing. So that's why they use the symbol B in the equation as well. But if you are ever writing this equation for your actual exam, you should write them in words. So once again, force experienced by a unit length wire carrying unit current placed perpendicular to magnetic field lines is the magnetic field strength of the magnetic field, which is given by unit equals to Tesla. 1 Tesla equals to 1 Newton per meter per ampere, or you could write Newton per ampere per meter, doesn't matter. And this is a vector quantity because force is a vector quantity. So magnetic field strength is also a vector quantity. It has a direction dependency. Yes, I'll take questions. Sajid bolo.
স্যার ওই আপনি যে বলতেছিলেন না F equals to F is proportional to rate of change of momentum, আমরা শিখছিলাম AS এর F equals to rate of change of momentum.
Yes, we did learn F equals to rate of change of momentum but that was not the law. Newton's second law, but as Isaac Newton defined it in his book Principia de Mathematica, blah 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 blah. He said that this is proportional. I mean, actually, he did not say this. He actually said the other way around. He said this one: rate of change of momentum is directly proportional to force. That's what he said. I actually wrote it wrong. The k was supposed to be here. So yeah, we actually learned that rate of change of momentum is equals to force, because by choosing this, making this whole thing happening, we make this constant k to become 1. Because the constant could become 1, that proportionality could be written as equals to. That's the
ও
mathematical trick that we did.
ও আচ্ছা 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 ওকে ওকে। আর স্যার ওই ডিটা কি ওই ইলেকট্রিক ফিল্ড স্ট্রেন্থ মানে ইকুয়ালস টু যে মানে আমরা এএস এর যে ইলেকট্রিক ফিল্ড স্ট্রেন্থ শিখছিলাম ওইটা,
কোথায়?
ওই এএস এর যে আমরা ইলেকট্রিক ফিল্ড স্ট্রেন্থ শিখছিলাম যে কি ফর্মুলা ছিল ভুলে গেছি, ভি বাই ডি না সামথিং সেটা ছিল এরকম।
হ্যাঁ, বি তো হচ্ছে ম্যাগনেটিক ফিল্ড স্ট্রেংথ।
ও আচ্ছা ম্যাগনেটিক ফিল্ড,
ম্যাগনেটিক ফিল্ড স্ট্রেংথ, নট
আচ্ছা আচ্ছা
ইলেকট্রিক ফিল্ড স্ট্রেংথ। দে আর ডিফারেন্ট স্টাফস। বাট ওই দুটো খুব কমনলি ইন্টাররিলেটেড। এটা রিলেশনশিপটা আমরা একটু পরে দেখবো, আসবে, ডোন্ট ওয়ারি।
আচ্ছা আচ্ছা। আর স্যার এই নোটটা কি গ্রুপে দিচ্ছেন?
না, এই নোটটা এখনো গ্রুপে দেয়নি। এই নোটটা আর একটু এডিট করা লাগবে, তারপর গ্রুপে দিব।
আচ্ছা স্যার ঠিক আছে, থ্যাংক ইউ।
শিওর। আচ্ছা, সবার এই ডেফিনেশনটা বোঝা গেছে ক্লিয়ারলি? এনি কোশ্চেন সো ফার? ইয়েস, আবিয়াস বলো।
Sir, we're defining this for a wire which is of, let's say, I don't know how much thickness, but what if we define it in terms of a cylinder or a plate or something like that, sir?
As per the definition, the definition is not dependent on the shape of the magnetic shape of the conductor, which would mean that we can choose any shape of the of conductor that we want. It wouldn't matter, but by choosing the material and the dimension and the voltage across that conductor, we have to make sure that the current that flows to that conductor has to be 1 ampere. So if you change the shape with the bigger or the thicker wire or thinner wire, then you have to essentially you will be affecting the resistance of that conductor, which we know for a fact. So in that case, we're going to require to control the voltage that would be applied across the conductor in such a way so that the current can be maintained to be 1 ampere. It is the current that we are trying to make fixed.
Also, this is just a defining point to fix the Tesla at a certain level, certain point to define the
Exactly.
Tesla.
The current has to be the defined point. Other variables you can manage on your own. For example, someone can recalibrate how much is 1 Tesla using a copper wire. Some other people in the other part of the wire, they can try it by some aluminum wire. It can happen. Both of them are equally correct, because the choice of material is not a factor. As long as you are making sure the current is 1 ampere, choice of material, dimension of material really does not matter.
Okay, sir.
Okay. Yeah, Sajid bolo.
স্যার আমার আরেকটা কোয়েশ্চেন ছিল, সেটা হচ্ছে এখানে আপনার সাইন থিটা হয়েছে কারণ আমি ভার্টিক্যাল কম্পোনেন্টটা শুধু নিব, তো হরাইজন্টাল নিলে আমার জিরো হয়ে যাবে, মোশন হয়ে যাবে, এই কারণে।
Yes.
আচ্ছা আচ্ছা আচ্ছা।
ওই জন্য সাইন থিটা আমরা নিচ্ছি, because we really want the perpendicular cross section or perpendicular intercept to work. That's what gives us the actual force. আচ্ছা, সো এখান থেকে আমাদের 1 টেসলা ডেফিনিশন দেওয়া আছে। ডেফিনিশনটাকে দেখো: if 1 meter long wire carrying 1 ampere current placed perpendicular to magnetic field lines experience 1 Newton force, then the magnetic field strength of that field is 1 Tesla. Or I mean, if you don't want to start in this way, you can also start in a different way. I'm stating this for your better understanding. The magnetic field within which you can start with the magnetic field word. The magnetic field within which 1 meter long wire placed perpendicular to the magnetic field lines carrying 1 ampere current experiences 1 Newton force is the magnetic field with 1 Tesla magnetic field strength. You can also define it like that. I mean, the actual placement of the words are not very important, that how you place them, but the inclusivity is important. You have to say all of the parts, that the length of the wire has to be 1 meter, the wire has to be placed perpendicular to the magnetic field lines, the current has to be 1 ampere, uh, and in that case, if the total force experienced by that wire is also 1 Newton. So you have to define 4 of these variables in any sequence you want. In that case, the magnetic field which is causing that thing to happen is defined to be of 1 Tesla magnetic field strength. This similar idea can be also applied for a single charged particle that is going to move across a magnetic field line. If you think about where does a single charged particle come from, one of the very simple way to create a charged particle is the electron gun. If you guys have remember this from your O levels, that in the cathode oscilloscope, we had an electron gun. By doing thermionic emission, we could produce free electrons out of a metal filament, and then by using an accelerating voltage of kilovolt rating voltage supplies across the cathode and anode, with a small hole at the center of the anode, we could produce a very sharp beam of electron, which we call the electron gun. So this is just one example of how we can make charged particles, but there are many other ways to make individually free charged particles which are going to move around in a specific direction or around a certain direction. Is possible to create by other mechanisms as well. So force on a charged particles moving through a magnetic field. This topic is mostly about, we are going to shoot a charged particle across a magnetic field. We're going to shoot a charged particle across a magnetic field, and as that charged particle is going to cut across the magnetic field lines and move through the magnetic field, it's going to experience some force. Because of the force, the path of the charged particle will definitely deviate. This goes without saying, and this is definitely going to happen because that force is going to work on the movement. And one thing is pretty interesting for you to understand is that magnetic force on a charged particle will always cause it to go in circular motion. I'll show you why. Everyone, try to make the famous left hand rule gesture in your left hand. First, define your left hand, which is on your left side, and then make the famous left hand rule gesture with your 3 fingers. If you have done this already, you should remember that your thumb represents the force direction, your index finger represents the magnetic field direction, or magnetic field lines direction to be more exact, and your middle finger represents the current. What you need to understand, the charged particle flow movement or the velocity of the charged particle, that is a direct representation of the current flow. How? If the charged particle itself is a positively charged particle, for example, a helium nucleus, alpha particle, then it's a actual flow of positively charged particle. Then the direction of the helium of the alpha particle and the conventional current is same, because conventional current was defined as the hypothetical flow of positively charged particles, which is actually not the truth, but that's why I use the word hypothetical. So conventional current is the hypothetical flow of positive charges. So in regular terms, if you have a positive charged particle flowing in any direction, conventional current is in that direction. If a negatively charged particle is flowing in any direction, conventional current is exactly opposite to that direction. So try to think about it. Let's say there exists a certain charged particle which is moving. So at a certain instant of time, you can define its velocity vector. At a certain point of time, you can define its velocity vector. So a particular instance velocity vector এদিকে. ওই charged particle টা, if that charged particle is positively charged, then the current is also going in that direction. If that charged particle is negatively charged, then the current is going in exactly opposite direction. Do I make sense about the plus and minus sign variation? এই জিনিসটা বুঝা যাচ্ছে?
জি স্যার।
So could you repeat?
What I'm trying to get in your head, what I'm trying to tell you is that we can what is current? Current is the flow of charge. Current is the flow of charge. So it is not imperative that we must have a conductor and bunch of charged particles should flow through that conductor and give us a current. It's not essential. A single charged particle flowing through space can also be defined as current, because that is also movement of charge. So if you have a positively charged particle going in any direction, conventional current I can be considered in that same direction. If a negatively charged particle is going in any direction, conventional current should be considered in the exact opposite direction of that velocity. That's what I'm trying to make. বুঝে গেছে?
Yes, sir.
আচ্ছা, I hope বাকিরা বুঝতেছো, because either you are not responding because it's clear to you, you are not trying to add noise to the channel, which I really appreciate, like superbly appreciate. Or if you have question, you can raise hand, you can write in the chat window. I have both of them open on the right side somewhere over here where you cannot see these. There's an empty blank space, but I have the participant list over here, I have the chat window over here. So yeah.
স্যার
Yes.
স্যার আমি বলছিলাম কি যে বিভি সাথে ওটা কি লিখছে মাঝখানে?
Q.
কিউ মানে
Yeah.
চার্জ।
This kid actually wrote their Q in this fashion. And bam, I don't know why. I'm not sure.
Basically wrote V for velocity, or am I right?
I'm about to start to describe this figure. I didn't yet start to describe this figure. I'm about to start. So let's have a look. We have the equation over here. Then we have a bit blurred picture over here, but it will make sense to you anyway. I can zoom in. Force on a charged particle moving through a magnetic field. আমি যে জিনিসটা বলছিলাম সেই জিনিসটাকে বলে শেষ করি. I asked you to make the famous left hand rule gesture in your left hand. So do that once again and try to understand. The thumb represents the force direction. The index finger represents the magnetic field direction or the magnetic field orientation, and the middle finger represents the conventional current. What I really want you to see, that this Flemish left hand rule is held true for any case. All of these three directions are always perpendicular to each other. What I really want you to appreciate, that the velocity vector, velocity direction, and the force direction are always perpendicular to each other. Am I correct? The middle finger and the thumb, they always have an anti-degree between each other. ठीक ना?
Sir.
This means whenever any charged particle starts to experience a magnetic force, it will experience that force perpendicular to the velocity. Whenever any charged particle, I'll say this again, whenever any charged particle starts to experience any magnetic force, that force will always be perpendicular to its velocity. This will essentially mean if any force is perpendicular to the velocity, what kind of motion can we anticipate? If the force is perpendicular to the velocity, what kind of motion do you anticipate? Circular motion? Because that's the very basic of circular motion, that whenever any charged particle, whenever any motion is such that the velocity and the force are perpendicular to each other. So that's what we call centripetal force, and it goes on further from there, but I'm not getting into that in detail. But you should know this, that if the velocity and the force are perpendicular to each other, that gives rise to what we know as circular motion. So that's what I'm trying to mean, that whenever any charged particle will experience a magnetic force, it will always try, at least try, to create a circular motion, perfect circular, which will have a radius, definitive radius, not a parabola, not an arc. So that's important, which is going to be helpful for us in the later part of the syllabus of the second. So once again, we have the figure over here. This, the force experienced by the charged particle is given by F equals to VVQ sin theta. I'm going to say what this figure contains. This is a magnetic field orientation, which is B. B should be represented as a vector quantity over here, so it might as well be logical to give a bar sign above over here, and velocity should also have a bar sign above over here. But for simplicity's sake, we did not do this, not to give you some confusion, but you should know this, that B is a vector quantity. In this case, velocity is also a vector quantity. This is not speed, this is the velocity. So let's assume a positive charge particle of charge plus Q is being shot in this direction. This is the velocity direction of the charged particle, which is about to enter, not already have entered, about to enter into the magnetic field. And this is the starting point of the magnetic field. The velocity line, if we extend this further, we can find out that if this produces an angle of theta with the magnetic field lines over here. So we can write that F equals to BVQ sin theta, which works out. So the force, whenever this charged particle will enter into the field, that force experienced by the charged particle is given by this equation, F equals to BVQ sine theta. Once again, the derivation of this equation is not given in your syllabus, so I'm not showing the derivation. If you're interested, I can direct you to the necessary literature where you can see the derivation of these things. It's possible. Stick to the class after the recording is done, after 9:30. So F equals to BVQ sine theta is the force that this charged particle is going to experience. Once again, we actually have done a lot of things over here. Okay. 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 Uh-huh. Wait. Wow. আচ্ছা। Pulman, did I ever show you the induction cooking? Wait. দাঁড়াও। So I have a lot of videos from here. This is the first thing that I'd like you to see. So, did any of you recognize the music?
It's the coffee carry music, sir.
Like এখন শুনতে অনেক সুন্দর লাগতেছে।
Yeah, do you want to hear it whole? It's one.
Yes, sir. I want this entire damn video.
Sir, induction.
Okay, check out. I have a lot of weird stuffs over here.
Sir, এটা link দেন।
Nah.
হ্যাঁ স্যার লিংকটা দেন।
Nah.
Please দেন না স্যার। অনেক পছন্দ বিউটিফুল। Please স্যার।
এটা আমি ইয়াতে শেয়ার দিয়ে দিব, এটা ছোট।
এক গ্রুপে দিবেন।
ঠিক আছে, এটা ছোট।
জি।
2.5 MB।
আসলে এটা অনেক ভালো দিয়ে লিংকটা।
এখানে আরো কিছু অসাধারণ ভিডিও আছে। আগামী
And they used it as a funeral song.
Yeah, but it's so this is aluminum silicon sealant. This is a half beaker or something. This is a very small beaker stand, and these are all magnets, and this is a motor which is going to rotate these magnets. See what's happened. is the other figure. It's playing all the videos that I have. You might as well see this thing. This is one of the very amazing animation that I found in Emag. And then we have ultrasound cleaning. Yeah, this I stored for the O-level syllabus. This is ultrasound chamber with certain coolant, cleaning fluid, and it's being
Yes, it came up on my feed a few days ago.
Yes, I usually share these stuffs, and then it's all cleaned up.
This is oddly satisfying, honestly speaking.
It's true, and it's just fresh and new. And then there's this billiard pool shot scene, which is just a random video. Anyway, so
করলো কিভাবে
কোনটা?
ওই পানিটাকে কিভাবে বল করলো?
That water was being vibrated at ultrasound frequency with some mechanism that is placed on the side or the bottom of the container, and that fluid had some very microscopic particles which could work as an abrasive. That's what this blue fluid was all about. Once you place it over here and turn on the supersonic thing, all the fluid vibrates supersonically. Sorry, supersonic. They move vibrate ultrasound, ultrasound frequency. They practically rub off all the surface intrusion from that ring, and that's how it gets cleaned. It's like small nanobots rubbing off the surface of the ring for nanometer dimension, but there are billions of them working together, cleaning up the whole thing.
না না আমি ওটা বলতেছি না, আমি বলতেছি বয়েল করছে কিভাবে পানিটা?
Acha, that was done by eddy current, which you're gonna see in a bit.
ওই যে আপনার মেটাল ডিটেক্টরে যেটা ইউজ করা হয়,
metal detectors also work with a bit of eddy current mechanism. That also works. আসবে eddy current কিছু ডিসকাশন পরে আসতেছে। আমি জাস্ট তোমাদেরকে দেখাইছি তোমাদের ইন্টারেস্ট গ্রো করার জন্য। And then the other video that I have is serious. We don't want to see that right now. Okay, never mind. কি দেখাতে যাচ্ছিলাম? চার্জ পার্টিকেল ফ্লো এখানে। আচ্ছা, এখান থেকে আমরা যে ইকুয়েশন গুলো পাবো, when theta equals to 90 degree, then F equals to BVQ, or that can be used as FC, which I just described. That this can be considered, this can be also considered as a centripetal force, because it's going to be always be a circular motion. So BVQ equals to FC equals to mv square by r. This m is the mass of the charged particle, v is the velocity, r is the possible radius of the circular path, which is not shown in this figure, because this particle is going to either bend out of the page or into the page, depending on the charged particle. Can somebody tell, is this in which direction this charged particle is going to bend by using Fleming's left hand rule? Tell me, is it going to bend into the page or is it going to bend out of the page? Try.
out of the page.
Into the page. Sorry.
Out, no?
Well, align your index finger. Align your index finger with the B. Then rotate your arm, keeping your index finger orientation same. Keep the index finger orientation same, and then rotate your wrist so that your middle finger aims with the velocity. Then your thumb should aim into the page. তার মানে চার্জ পার্টিকেলটা ম্যানিফিল্ডে ঢোকার পরে ভেতরের দিকে বেন্ড করে যাবে। ঠিক আছে? So yeah, when theta equals to 90 degree and then F equals to BVQ, F equals to mv square by r. So we can get this equation right. And what we can get from here, I mean, this is actually a pretty interesting mathematics. I'm going to explain this in a bit. Hold up. BVQ equals to mv square by r. এখান থেকে VRV cross out হয়ে যাবে, একটা square বাদ চলে গেছে. So if you do the ratio of Q by M, we get V by BR. Q by M equals to V by BR. Now, if I subject R, so এই বক্স করা ইকুয়েশনটা আমাদের বিভিন্ন সময় ম্যাথমেটিক্সে অনেক ধরগুলো ম্যাথের জন্য কাজে লাগবে, জন্য ইকুয়েশনটা বক্স করা আছে। ফার্দার ডাউন দ্য লাইন এখান থেকে যদি আমরা R কে সাবজেক্ট করি, এই পুরো ইকুয়েশন যদি R কে সাবজেক্ট করি, we're going to get V divided by B, if we take the R and one, and this whole Q by M is gonna be come below this thing. Now here comes some set of calculation. I'm gonna explain this just a second. R equals to V by B into 1 by 4 by M. এই 4টা আসছে কোত্থেকে? Where did this 4 come? So এটা 4 না, এটা Q হবে। আমার লেখায় হয়তো এটা 4 দেখা গেছিল, maybe I did write it wrong. এটা Q হবে, এটা আমি এডিট করে ফেলি এখন। এটা Q কেমনে বানাবো? এটারে Q কেমনে বানাবো? Type text. Oh, that's a big Q. Okay. And I wanted to have some background. And ঠিক আছে না? বলবান এটা বুঝবা তো?
Yes, sir.
Yes, sir.
Yeah, it was my poor handwriting, I believe. Otherwise, the kid is not supposed to be mistaken. So it is Q by M. এখন what we're gonna do is that we're gonna try and consider the possible bending radius comparison between a alpha particle and a beta particle. Try to think about it. If you shoot one alpha particle into a magnetic field and one beta particle into a magnetic field with equal initial velocity, which is going to bend more? We're going to see some possible comparison for those two measurements. Let's say for alpha particle, the mass is 4m. I'm assuming this m to be a u. এখানে u লিখলেও হইতো। And the charge of alpha particle is plus 2e. For electron, the mass of an electron is about 1 by 1800 of m, or electron is about 1 by 1800 times lighter compared to the atomic mass unit. I should have written u over here. Should I write u over here? I should write u over here. I might as well try to write u over here. And also, do you guys know what u is?
Atomic mass unit.
Atomic mass unit, yes. So the alpha particle mass is about 4u, whereas the mass of one electron is about 1 by 1800 u. So these are the two, and the charge of one electron is minus e. Yeah, Joshim, Mamun, এটা on করো তো। Mass of an electron is e, so it is written as minus e. Minus this কারণ হচ্ছে এটা minus আমাদের লাগবে, just to understand that alpha particle and beta particle, they are going to bend in two opposite directions. That's where the plus and minus comes in. Anyway, now if we calculate the ratio of q by m for alpha, if we calculate this ratio q by m by alpha, we're getting 2e by 4u. So that is, we're getting half 1 by 2 e by u. And over here we are getting q by e m of electron, that would be e divided by 1 by 1800 u, that is 1800 e by u. So if we try to get a ratio of these two quantities, so q by m of alpha divided by q by m of electron, q by m is a specific quantity, it's called specific charge, which is electropolar. A ratio of 1 by 3600. 1 by 3600. Q by m is called the specific charge of a particle. Q by m of alpha is really small, only half of e by u, and q by m of e is very big, 1800 e by u. E is a constant, u is also a constant. So these are two constants, so they are going to have some numerical values, whatever. But we're trying to compare these two things in terms of this multiple. So radius of alpha is very large. Why radius of alpha should be very large? Because have a look, r equals to v by b into 1 by q by m. This denominator is just being very small, means r will be very large. Denominator being very small, why? Because this is half of e by u. Compared to for the electron, this is 1800 e by u. So for electron, this denominator is very big. So the r would be very small. Vice versa for alpha particle, this denominator is very small. So the r, or the curvature of radius, the radius of the bending would be very large. So r alpha is very large, that is curvature too small, acceleration small, and vice versa. Numerically, r alpha is about 3600 r electron. এখানে r electron লেখা হওয়ার দরকার ছিল, এটা এখানে ছবিতে কাটা পড়ে গেছে. I'm sorry about that, but you get the point. Radius of alpha should be about 3600 times as big as the radius of a beta particle. This is also why we usually see, we not usually, we are shown some figures that are, this is why we used to see figures like these. These figures are not drawn to scale. These are just comparable representation for how the figures are supposed to be. Gamma should not have any deflection whatsoever. Alpha is going to have a very small deflection, but it's going to have some deflection. Whereas beta is going to have a very sharp deflection, which means this is going to bend really, really strongly. Having a bend very strongly essentially means that this has a very large amount of centripetal acceleration, or its radius is about very small compared to the radius of alpha. So that's reason why we had this kind of figures. আমরা এই রিজনিং গুলা ও লেভেলসে থিওরি ওয়াইজ পড়ে আসছি, এখন আমি তোমাদের কিছু ক্যালকুলেশন দেখাইলাম, কারণ এটা ক্যালকুলেশন বেস আমাদের কিছু ম্যাথমেটিক্স সামনে আসবে, ওয়ার্কশিট করার সময় আমরা পাবো। এই পার্টটা বুঝা গেছে সবার? I'll take question. শুভ্র বলো।
ও স্যার আমি নামাই দিচ্ছি, থাক ওটা পরে আগে ছিল আর কি।
ঠিক আছে, সাজিদ বলো।
স্যার আমি এখন পর্যন্ত বুঝতেছি না কেন সার্কুলার মোশন হবে, আমার কাছে মনে হচ্ছে প্রজেক্টাইল মোশন হচ্ছে।
বলি, প্রজেক্টাইল মোশনের বেসিক শেপটার নাম হচ্ছে প্যারাবোলিক মোশন। প্যারাবোলিক মোশনের বেসিক কনসেপ্টটা হচ্ছে ইররেসপেক্টিভ অফ দ্য ভেলোসিটি, initial, final, instantaneous, doesn't matter. Irrespective of the velocity direction of the particle, the force will always work in one single direction. The force will not change with the change of velocity direction. For example, whenever an object is thrown in parabolic in projectile motion, the weight always works vertically downwards, irrespective of the velocity of the object. Object going upwards, vertically upwards, diagonally upwards, downwards, whatever. Force is always working in one single direction. What is that? Downwards. But if you think for magnetic force will always happen in such a way that the velocity and the force will always be 90 degrees to each other. Whenever the velocity will change, the force will also change. The figure can be somewhat like this. আমি তোমাকে একটা ফিগার দেখাই। এই যে দেখো, if you have a look at this figure, try to understand. Let's say a certain charge particle is going around in circles like this. Whenever the velocity is this way, the force is perpendicular in this way. Whenever the velocity changes, the force is also going to change in such a way that the velocity and force will always maintain 90 degrees between each other. That's what gives rise to the circular motion. বুঝছো কি?
হ্যাঁ, তার মানে কি বেসিক্যালি ধরে নেন একটা বেটা পার্টিকেল যদি অনেক বড় উইথ একটা ম্যাগনেটিক ফিল্ডের ভিতরে ঢুকে ও সারা জীবন ওটার মধ্যে আটকে থাকবে।
ইয়েস।
তার মানে কি, আমি যদি ধরে নেন ওই বেটা পার্টিকেল মানে হচ্ছে ইলেকট্রনিক ফ্লো মানে হচ্ছে এখানে স্পার্কস ক্রিয়েট হওয়া, তাই না? ন্যাচারালি মানে একটা ফিজিক্যালি আমরা যেটা দেখতে পাবো। তাই তো?
ওকে,
তো যদি আমি বলি যে এরকম তো অনেকগুলো বেটা পার্টিকেল আছে, সো ওরা এরকম ঘুরতে আছে একটা সোর্স থেকে, ধরে নেন বেটা পার্টিকেল দিতেছি, ওই জায়গার মধ্যে ঘুরতে আছে, তার মানে ওই জায়গার মধ্যে অনেক হাই একটা কারেন্ট ভ্যালু আসতেছে। সো ওইখান থেকে আমি একটা সোর্স নিতে মানে ওইখানে কি মানে আমি আমি আসলে পুরা ফেলছি কোশ্চেনটা।
বলতেছি, you are trying to speculate something about an infinite source of energy, am I correct?
হ্যাঁ,
Well, hypothetically it's possible, but practically it is not. I'll tell you why. For that beta particle to move around continuously in this circular motion, you would require some conductor or you need require some medium through which, by which you could possibly absorb out that energy. Whenever you will take out some energy from this moving charge particle, you're going to slow it down. The moment you're going to slow it down, because the kinetic energy has to be taken out as electrical energy, one type of energy converting to another type of energy, and the moment you're going to slow it down, you're going to have a bigger radius of circle. That's going to give you some trouble. So this is a bit of a problem that we have. I mean, we can have it, but we cannot have it indefinitely. The superconductor is an idea. Superconductivity is a pretty cool thing, where the resistance of an object is practically zero. That can be used to achieve extremely high amount of current over a very small space, usually applicable for to produce a very strong concentrated magnetic field, usually used for linear accelerator or cyclotrons for particle breakdown researches. But that can also give us a limited amount of energy loss. We can reduce the energy loss so that it is practically possible for us to produce such a high amount of current within such small space. But that is also not a practical way to have infinite source of energy. But to be honest, there is nothing called an infinite source of energy. Every type of video that you see in YouTube videos, which have, like, many of them have millions of views, they are all practically dumb, and many of them were actually debunked by the Ya channel, this guy who always gets shocks, Electro Boom. He debunked a lot of these videos, that how those things were working. Yes, fine, bolo.
স্যার ওটা বুঝলাম না কেন ওই যে ইনফিনিটি অ্যামাউন্ট অফ এনার্জি আসবে না ওই যে ওইখান থেকে যেটা সাজিদ বললো, মানে কেন পসিবল না?
Infinite amount of energy হওয়ার মানে হচ্ছে you are gonna have infinite amount of energy available to you, so that you can extract energy out of it indefinitely, but the total amount of energy of that thing will not reduce. That's what we mean by indefinite energy, right? Or infinite
হ্যাঁ,
energy. But whenever you are going to try to extract some amount of energy, electric energy out of it, you're going to be converting some amount of energy available to that beta particle or electron, let's say, into some other kind of energy. And what kind of energy should that beta particle give out so that you could use it for your other purpose? It has to be its own kinetic energy, because its own kinetic energy is what it has. Whenever it will give out its own kinetic energy, it is definitely gonna start to go out in a much bigger radius circle. Why that radius is gonna be bigger? We have talked about this in our circular motion chapter. যে kinetic energy কমে গেলে radius কেন বড় হবে, মনে আছে?
স্যার একটু ভুলে গেছি, একটু বলতে পারবেন আমার মানে?
বেসিক্যালি লেন্সেস ল হচ্ছে।
No, not, I didn't say Lenz's law. বন্ধ। দাঁড়াও, আমি এখানে আসতেছি, কারণ হচ্ছে এখানে একটা কোন একটা কোশ্চেন এটা অলরেডি ছিল আমাদের ক্যালকুলেশন, আমি দেখাই দিচ্ছি, দাঁড়াও। এই যে for the satellite iron is the expression is of GMMR for scanning energy and gravitational energy. So এখানে আমরা দুটো এনার্জি হিসাব করে বের করছিলাম, and then there was this thing, the total energy of the satellite gradually decreases, and this has the effect on the decrease on the radius of the orbit. The radius of the orbit is gonna increase, as far as I can remember, to 5c1. Oh no, R is gonna become decrease. Oops. আচ্ছা, R will decrease and V will increase. আচ্ছা, এখানে তো আমাদের পটেনশিয়াল এনার্জি ইনভলভ ছিল, আমাদের ওই ইকুয়েশনে তো পটেনশিয়াল এনার্জি ইনভলভ থাকবে না। সরি, বলছি এই ইকুয়েশনে তো আমাদের পটেনশিয়াল এনার্জি ইনভলভ থাকবে না। ওইখানে তো গ্র্যাভিটেশনাল ফিল্ডের জন্য একটা পটেনশিয়াল এনার্জি ইনভলভ ছিল এবং কাইনেটিক এনার্জি দুটো ইনভলভ ছিল। সো আমরা টোটাল এনার্জি নিয়ে কথা বলতেছিলাম। বাট whenever if we are trying to extract energy out of an infinitely orbiting electron, we are going to slow it down. The moment we are going to slow it down, try to think about it. F equals to mv square by r, and v যদি আমরা কমাই ফেলি, আমরা যদি v টাকে কমাই ফেলি, টু বি অনেস্ট v স্কয়ারও কমবে। এখন v স্কয়ার কমে গেলে আমাদের ইকুয়াল অ্যামাউন্ট অফ fc অ্যাভেলেবল থাকার জন্য rটা কি হতে হবে? বড় হতে হবে না কমতে হবে?
বড় হইতে হবে। না না না, কমতে হবে।
কমতে হবে, সরি, হ্যাঁ কমতে হবে। কমতে হবে না?
জি স্যার, কমবেই তো।
হ্যাঁ, সো রেডিয়াসটা কমে আসবে। and radius যদি কমে যেতে শুরু করে, তার মানে কি eventually the electrons are not going to be able to maintain their original radius. Whenever the electrons are not able to maintain the original radius, it means what? You do not have the exact same state that you started with. So slowly the radius of the electrons are going to slowly become less and less and less and less, and eventually you are going to end up with a zero radius of electron, which means the electrons are not moving at all. So basically you're not having an infinite source of energy. The electrons which are moving in that circular orbit with some specific amount of kinetic energy, you can extract that amount of kinetic energy out of them, and after they are done delivering you that kinetic energy, you are practically have those electrons stationary at the center of that circle. They're not going to move anymore. So it's not an indefinite source of energy. It's not an infinite source of energy. It's not going to work as an infinite source of energy. It doesn't.
ওই ইলেকট্রনটাকে কিভাবে সরাবো?
ম্যানিফিল্ডটাকে অফ করে দিলে ইলেকট্রনটা পড়ে যাবে। or you can just have a charge arrestor or a net or something like that. বুঝছো এই জিনিসটা?
আচ্ছা স্যার, যে যতটুকু আমরা এনার্জি এক্সট্রাক্ট করব ততটুকু আবার কি অ্যাড হবে না? কারণ আমরা তো ইলেকট্রনস মানে গান থেকে তো বের হইতেই আছে, এটা তো থামতেছে না।
কারণ যে গান থেকে আমরা বের করতেছি সেই গানের মধ্যে তো আমরা কিছু এনার্জি খরচ করতেছি। একটা অল টুগেদার ফ্রি এনার্জি ডিভাইস মানে কি, যে তুমি কোন এনার্জিটাকে ফিট করা ছাড়া তার থেকে এনার্জি বের করবা। একটা ইলেকট্রন গান থেকে তুমি যদি অলরেডি কাইনেটিক এনার্জি দিয়ে ইলেকট্রনকে শুট করতেছো, তার মানে তুমি তো ওখানে এনার্জি অলরেডি খরচ করতেছো না?
হ্যাঁ
ঠিক আছে, যেমন আমি আরেকটা সার্টেন ভিডিও দেখাই, মানে এই টাইপের ভিডিওগুলো অনেকের জন্য পারপ্লেক্সিং মনে হতে পারে। ইটস ইন্টারেস্টিং the idea of free energy and everything, so that's why I'm covering this topic with such enthusiasm.
If you are like me and have a spare PC fan lying around, then it is always a good idea the power of around thus not a which represent the two coils. It's the capacitor
স্যার,
বলো।
আপনি যে বলছিলেন আপনাকে কপিরাইট করে, so you would stop the recording when showing us videos?
No, I try to give the credit in the description in applicable cases. Acha, what this video is about, he has connected some small magnets in the rotor blades of this fan, and then he's gonna bring up another magnet over here and place that magnet in such a way that it is gonna apply some force onto these magnets, and as a result these magnets are gonna start rotating. These magnets are gonna get this force and they're gonna start rotating and produce out some energy out of this thing. Now here's the deal. The only reason this whole process can work is because you have the existence of these magnets arranged in a very specific way onto this device. you have to ask yourself that how did this device come into existence? Did the magnets come into existence? These strong magnets that you have existing over here come into existence naturally? এই ম্যাগনেট গুলাকে ম্যাগনেটাইজ করার জন্য তো কিছু না কিছু অ্যামাউন্ট অফ এনার্জি খরচ করতে হয়েছে না? Think. To manufacture these magnets. So basically what did we do? We sort of stored a huge amount of electrical energy within these magnets by arranging those dipoles. This is not defined as a value, as a type of potential energy, but it is a type of potential energy in my opinion, because we can get some of these energies out by having this rotation done continuous. Now this is what's going to happen. If you make this rotate to keep on rotating indefinitely, you're going to get some current out of these two wires that he is having in this coil. You're going to get some current. You can measure how much total energy you can get out of it. Over the time, as the magnets will keep going around in this magnetic field, they are going to continuously go across a strong and a weak magnetic field. So basically, the type of demagnetization effect that we have read earlier in the O-level syllabus, that there are 3 ways of demagnetizing a magnet. Number 1, hammering. Number 2, heating. Number 3, placing a magnet within a alternating magnetic field. Remember? So
yes, sir.
Whenever you're gonna place this magnet in this way, have a look. Here he is having let me bring up this frame. Here he's holding this magnet over here. So he is making a fixed magnetic field over here, but these magnets are continuously rotating, which means whenever the magnets are over here, they're under the effect of a strong magnetic field because of this. And then whenever they're traveling over here, they are under the effect of a weak magnetic field over here. They're continuously rotating, which means they're continuously going across in an alternating magnetic field orientation, which means little by little, small by small, each of their dipole arrangements are slowly becoming disturbed. Over a period of usage, all of those permanent magnets are going to definitely slowly lose their permanent magnetism. This is not an indefinite source of energy. This source is only going to work as long as all of those magnets have enough magnetism left within themselves so that they can overcome the friction of the generator, that unit that he has at the center. Whenever they will lose their magnetism to such amount that they can no longer do this thing, then it's going to stop. And if you calculate out how much energy could you possibly get out of the system versus how much energy was used up in the first place to make all those magnets into magnets, you are going to end up to have a much smaller amount of energy output from a device like this. Do I anyhow make sense?
Yes, sir.
Yes, sir.
So there is no such thing as free energy. I mean, you can buy stuffs, that's another thing, but having a free energy in terms of physics is, as long as I know, not gonna happen. One of the things that I always thought about free energy could happen is by means of siphon. Do you know what a siphon is?
Something that draws water out of something else.
Exactly, you can draw water out of something else. By using capillary action and siphon of water, I mean, I thought free energy could be available by means of the availability of the atmospheric pressure. But then I did some research, and this was back when I just graduated from my university. Then I did some research, and I did find out that this was a very largely attempt in a huge part of the scientific community, and it didn't work out for practical reasons. I mean, the more.
I have a question.
Huh?
I have a question.
Follow.
Since you're worrying about free energy, I'm sure you're aware of that when dark matter bursts, right?
Dark matter?
Sir, so there's this package of dark matter in the center of the universe. So when it bursts out, an anti-dark matter also comes out along with it. So when these two come out, there are gamma photons generated as well. So isn't that some kind of free energy?
Well, that's the thing. What I mean about free energy made available is applicable for our regular lifestyle requirements. What happens in a cosmic scale on a celestial happening is a totally different thing.
ডার্ক এনার্জির ম্যাপ ব্যাপারটা নিয়ে কিন্তু এখনো আসলে শিওর না, অনেকে বলছে এটা
Yeah.
ডিবাঙ্কড হয়ে যেতে পারে পুরা।
It's not
let,
dark
let,
energy I'm talking about.
let me put out my idea. What happens in a celestial case on a cosmic scale is not how we could possibly do this. I mean, the whole idea of Dyson sphere can be also considered as a free energy device. I mean, if you can have a Dyson sphere, I mean, you could absorb all the energy out of a star and get all the energy out of it. I mean, why not? But
Yeah.
these are models that we can talk about which are not practically achievable yet. Do I make sense?
Well, we could capture gamma photons with the Cherenkov Array telescope.
We could, but would that be usable to us? To what extent? I mean, if I put it in this manner, I mean, having
Sir,
free
have you
energy
heard of the Dyson
at its-
sphere?
I just talked about Dyson sphere. We I mean, having free energy at its core would essentially require us to have a mechanism that can possibly give us energy out of nowhere. I mean, using no resource whatsoever. I mean, if you think about it, I mean, if dark energy and dark matter does come out and the gamma photons are released, there must have been something from which those gamma photons did get released. I mean, up till now, we don't have the means or logic to observe dark matter. Up till now, we could not develop such observing techniques, observing equipments that could possibly measure or observe dark matter. But our calculations say that it exists, but we can see it. Might as well be in the fourth dimension, might as well be in the fifth dimension. So we are three-dimensional beings. We cannot understand that. Could happen. I don't know. But the thing is, even if that happens, I mean, would it be entirely possible that that is happening out of the cost of nothing? Like
You're
from
saying that something must have happened for it to be released.
that something might include something that is definitely perishable. That's my point. That's what I believe, but I might be wrong.
I get it.
Okay, Bolaban, a lot of the kids have left at the 9:30 mark, which I really appreciate because they followed protocol. Not a big deal. We're gonna start our next class from this point and go on further into the discussion. Thank you very much for your attention. I'm gonna pause the recording and did